particles. So here we will discuss the determination of energy of the free particle which is traveling in a one dimension without any obstacle. That is a particle that is not influenced by any force moving in one dimension. We can do same for particle moving in three dimension, and also we can also do same for the particle moving in two dimension. So here, so the first step is construct the appropriate Hamiltonian operator for the given system. That means here we will construct a proper Hamiltonian operator, that is the total energy operator, and formulate the wave equation for the problem in hand. And the second one is solve the resultant eigenvalue differential equation, Schrodinger wave equation, to obtain the general solution, and make the wave function obtained above to follow boundary conditions and normalize the wave function to obtain. And after that, generate energy expression for the system, then retrieve the value of dynamic variable for the above wave functions, and analyze the wave functions and energy expressions. Now, as in the initially we have stated that the particle will move freely in three dimensions without any obstacle. So that will move freely in three dimensions without any obstacle. Let us take the problem now and consider a single particle. So here we will consider that the mass of the particle is m, that is moving freely along x direction as shown below. So here this is the particle with mass m that will move freely in the x direction. So as it will move freely in the x direction, so the distance traveled by the particle will be from minus infinite to plus infinite. That means the value of x ranges from minus infinite to plus infinite along the x axis. As the particle will move freely, so the potential energy of so that means the particle will move continuously, and hence the potential energy of the particle will be zero, because the particle is in motion. In the absence of any force field, the particle is free to move anywhere along the x-axis. Since there is no external forces operating on the particle, its potential energy is constant and it can be considered to be zero. However, to keep the thing simple, we assume that the potential energy of the particle to be zero. And after that, we will formulate the Schrodinger wave equation for the free particle. Now, formulate the Schrodinger wave equation essentially involves the construction of the Hamiltonian operator of the system, because we know that the general Schrodinger wave equation is h cap psi equals to E psi. So here h cap is nothing but that is the Hamiltonian operator. And here, as we are considering the potential energy to be zero, that means here the total energy is equals to kinetic energy. So kinetic energy of the particle will be half mvx square, as the particle is moving along the x-axis only one dimension, that is in the x-axis only. So the kinetic energy will be half mv square, that is half mvx square. Here vx is velocity of the particle along the x-axis. So kinetic energy equals to half mvx square, which is equals to 1 by 2m m square vx square. That means here we are multiplying m in the denominator and numerator also. So that will become 1 by 2m m square vx square. So we know that mv is nothing but that is the mass into velocity, that is the momentum. So m square vx square, that is the px square, that is the momentum of the particle along x. Px is momentum of the particle along x-axis. So kinetic energy, that means the total energy, will be equals to 1 by 2m px square. Now substituting the quantum mechanical operator for linear momentum along the x-axis, because we know that So this is the quantum. So according to the postulate of quantum mechanics, the quantum mechanical operator for the linear momentum along the x-axis will be I h cross d by dx. So the kinetic energy operator will become, that is t cap equals to 1 by 2m. In place of px we should put this value, and the kinetic energy operator t cap equals to 1 by 2m px square. So in place of px we can write this one, that is minus I h cross d by dx whole square of minus I h cross d by dx. And the simplifying this, we can write the kinetic energy operator T cap equals to minus h square by 2m d square by dx square. Now, to get the Schrodinger wave equation, we substitute the expression for the Hamiltonian in the general expression, that is h cap psi equals to E psi. So, here, in place of Hamiltonian operator, that means in place of total energy operator, you have to put the kinetic energy only, because here we have considered the potential energy Vx, potential energy of the particle along x-axis, that is Vx to be equals to 0, and hence the total energy equals to kinetic energy. So in place of h cap, here we should put t cap, and hence the Schrodinger wave equation for the particle moving freely along the x-axis will become minus h cross square by 2m d square psi x by dx square, which is equals to E psi. Now solving the, so this is the Schrodinger wave equation for the particle moving along the x-axis freely. Now solving this Schrodinger wave equation, we can write, simplifying and so rearranging this equation, we can write d square by dx square psi x plus 2me divided by h cross square psi x equals to 0. And here the this one, that can be written as d square by dx square plus 2me by h cross square whole into psi x. So here in place of d square by dx square, we are just putting capital D square. Now the equation will become, now the operator will become d square plus 2me by h cross square. And solving this, we know that solving this, so we can write d square equal to plus minus 2me minus plus minus, from this equation 3.7 we can write d square equals to minus 2me divided by h square, and solving we can write d equals to plus minus of minus 2me square root of minus 2me divided by h cross, which is equals to plus minus I 2m square root of 2me divided by h cross. It implies that the two wave functions that satisfy the Schrodinger wave equation for the free particle moving along x-axis will be psi1 x. So two wave functions will satisfy this equation. So because here, so it is given that d equals to plus minus I whole into square root of 2me divided by h cross. So this value will give two values. So the value of d, there will be two values. It implies that there are two wave functions that satisfy the Schrodinger wave equation for the free particle. And the wave functions will be, solving this we can write the wave function will be psi x equals to a into e to the power minus I by h cross into square root of 2me x. and similarly psi 2 equals to, that means here we are putting the value of d as plus I square root of 2me divided by h cross, and again similarly if we put the value of d equals to minus I square root of 2me by h cross, the wave function will be like this. So these are the two wave functions for the particle moving along x-axis, free for the free particle moving along x-axis. So here we have solved the wave functions associated with the free particle moving along x-axis, and the next step is to apply the boundary condition on the wave function. So as there is the question is what could be the boundary condition here, because here there is no boundary, the particle will move freely, and hence the boundary condition of the wave function, that will be x tends to, or x will be equals to plus minus infinite. In this term, that require that the square root of 2me should be real. It can be shown that this is possible only if e happens to be positive or 0. So here psi 1, the first wave function psi 1 equals to a to the power a into e to the power minus I by h cross square root of 2m minus ex, that is equals to a into e to the power square root of 2me x divided by h cross. Since it has a positive exponent, it is a divergent function, that is it will go to infinite value for plus infinite values of x, and it is not acceptable. Similarly, we can check the second wave function psi 2x using e to be negative. So if we use e to be negative, then the second wave function will become like this, and here again the wave function become divergent when x tends to minus infinite. Thus we find that only the restriction energy, that is E, should be greater than equals to 0. That means it can take up any positive value. Thus the allowed energy value for a free particle that are continuous as in classical mechanics. It is important to note that in the case of free particle, there is no quantization of energy. So if no boundary will be there will be no quantization of energy of the free particle, will not be quantized. Now coming to the normalization of the wave function. So the normalization condition, we know that the normalization condition, so this is the condition of normalization, that is whole integration of psi star psi dx equals to 1. So for the wave function, for the first wave function, psi star will become a star e to the power minus h cross square root of 2me x, and psi already the first wave function psi is a into e to the power I by h square root of 2me x. So putting all this value, we can write the normalization condition to be like this, and here a is the constant, so a and a star are two constants, so that can be outside of the equation, so which is equals to a star a whole integration of e to the power 0, because here e to the power this much and e to the power this much, so that will be added and that will become e to the power 0, and hence e to the power 0 something to the power 0, that is 1. So the value will be a star into a whole integration of dx, that is equals to a star into a into, because we know that integration of dx is x and it is having value minus infinite to plus infinite, which is not equals to 1. That means no finite value of a which could make the integral equals to 1. And similarly, if we use the second wave function, this value will not equals to 1. Hence the wave function for the free particle cannot be normalized in the usual sense. So if the particle will move freely, the wave function cannot be normalized. Now coming to the retrieving the values of the observables. So here we know that, so this is the linear momentum operator px cap. So Px cap equals to minus I h cross d by dx operating over the wave function psi1, that means first wave function. If the linear momentum operator will be operated over the first wave function, then that will become Px cap psi1, which is equals to minus h cross d by dx. So this is the first wave function, and solving this we can find out that the value will be become minus square root of 2me psi1. And similarly, if we will use second wave function, and if the second wave function will be operated over the linear momentum operator px cap, the value will become square root of 2me psi2, and hence we get the momentum of the particle px equals to plus minus of square root of 2me. We have shown the above that the energy of the free particle will not be, that cannot be quantized, so it can take any positive value. Therefore as the energy will not be quantized, as the energy of the free particle will not be quantized, therefore the momentum will also not be quantized. However, here you may be observed that if psi1 will be chosen, if the first wave function psi1 is chosen, then the possible values of the momentum are negative, implies that the particle is restricted to move in negative x direction. Whereas the wave function, if we take the second wave function, that means psi2, the motion of the particle is restricted in plus x direction only. But we could, but here initially we have considered that the particle should be moved in a freely along the x-axis, whether that may go to positive x-axis or negative x-axis. So if two eigenfunctions psi1 and psi2 of a linear operator a cap have the same eigenvalue a, then any linear combination of the wave function will also be eigenfunction of the same operator a cap with the same eigenvalue. So this is the principle of eigenwave function. Therefore, we can generate a newly wave function by a linear combination of the wave function psi1 and psi2. Because as here we have observed that if we take first wave function, then the momentum will be negative. That means the particle will be restricted to move in negative x-axis. And if we take the second wave function, the momentum will be positive. That means the particle will be restricted to move in positive x-axis. But here we have initially considered that the particle should be free particle, and hence therefore, we can generate a new wave function which is a linear combination of psi1 and psi2. And the new wave function is psi x, that is psi1x plus psi2x. So here the first wave function plus second wave function. So this wave function represents the free particle that is allowed to move in the plus x axis as well as in the minus x axis. So here what so for this long question what we have discussed, the conclusion is there is no quantization of energy in case of the free particle, first condition. Second, the wave function of the free particle moving x-axis cannot be normalized in usual sense. The probability of finding of the particle is equal for all the values of x from minus infinite to plus infinite, which means that the position of the particle is completely uncertain. So this is about the quantum mechanical treatment of the particle moving freely along one dimension, that is along x-axis. Now coming to particle in one-dimensional box. So in the previous section, we have discussed the particle in moving freely along one dimension, but here box means some boundary condition will be there. That means some restriction will be there. So let us consider a particle of mass m that is allowed to move along x-axis. However, we restrict the motion into certain region by visualizing the places of infinite potential. So here that is a one-dimensional box. Box means some boundary will be there, and the boundary condition is the particle is allowed to move from x equals to 0 to x equals to L. That means the length of the one-dimensional box will be L. So these infinite potential region acts as walls of the particle and do not let it go past them. So here you can see, and here this is the one-dimensional box. This is the particle of mass m. The particle is allowed to move from x equals to 0 to x equals to L. That means within this region, that means when the value of x is greater than 0, less than L, the particle will move inside the box. And here we are considering the potential energy inside the one-dimensional box, the potential energy of the particle inside the one-dimensional box to be 0 because that is a moving particle. And on the wall, the potential on the wall and also outside the wall. So this is the wall. This is the left hand side wall where x equals to 0, and this is right hand side wall where x equals to L. So on the wall and outside the wall, the potential energy is considered to be infinite, but inside the box, the potential energy is considered to be 0. So there will be three different regions. For region 2, where the particle will move inside the box. For this region, the potential energy equals to 0 and the particle is allowed to move from 0 to L. That means the position of x is less than 0, x is greater than 0 and less than L. So this is called region 2. The particle will find in the region 2. And on the wall and for region 1, the particle cannot reach the wall and also that cannot move outside the wall. And hence, on the wall and outside the wall, that is for region 1 and also for the region 3, the potential energy is considered to be infinite. Now, here we will formulate the Schrodinger wave equation for the particle moving in one-dimensional box, and also we will solve that one. Now, the first step is to construct the appropriate Hamiltonian operator for the given system and formulate the wave equation for the problem in hand. Now, since the problem is quite like so that of the free particle, so here the Hamiltonian and the Schrodinger wave equation of the particle within the box, that means the region 2, here we will construct the Hamiltonian, the Schrodinger wave equation of the particle, and also we will formulate the Hamiltonian operator for the particle for the region 2. However, for region 1 and region 3, we will have to consider the potential energy to be infinite. Therefore, we can write the expression for the Hamiltonians and for the Schrodinger wave equation in the different region. For region 1 and 3, the Hamiltonian h cap equals to h cross square divided by 2m d square by dx, and this is the expression of the Schrodinger wave equation because we know that h cap psi equals to E psi. So the Schrodinger wave equation for the particle in region 1 and 3, that is minus h square by 2m d square psi infinite x by dx square equals to E minus infinite because E minus V. So here for region 1 and 3, the potential energy V will be infinite. So which is equal to E minus V psi x. And for region 2, the potential energy will be 0. And hence, so this is the Hamiltonian operator. And the expression for the Schrodinger wave equation will be like this. That is minus h square by 2m d square psi by dx square equals to E psi. Now solving the wave equation. So let us first solve the following Schrodinger wave equation for the region 1 and 3, because we know that for the region 1 and 3, the Schrodinger wave equation is like this. So in place of potential energy, infinite is there. So we can neglect the energy as compared to infinite, and so you can see in the RHS of the equation is E minus infinite psi. So the energy E can be neglected as compared to infinite, and hence this equation is converted to like this. So the equation 3.22 is converted into 3.23, neglecting the energy E as compared to infinite, and the equation will become minus h cross square by 2m into d square psi by dx square equals to minus infinite psi x. And simplifying and rearranging, we can write psi x equals to 1 by infinite d square psi x by dx square. So 1 by infinite value will become 0, and 0 into something, that is equals to 0. This implies that the wave function of the particle for region 1 and 3 is 0. That means the particle cannot move to region 1 and 3, and also that cannot move to the wall, because when the particle will move to the wall or region 1 and 3, its wave function will become 0, and hence we come to the region of interest. So our region, so details we will solve for the region number 2. So the wave equation for this region is the same as that of the free particle, and the wave equation will become minus h square by 2m d square psi by dx square equals to E psi. Since the Schrodinger wave equation for this region is identical to that of the free particle, and hence without solving here, we can use what we have solved for the free particle, the two wave functions to be like this. The first one is psi 1 equals to a into e to the power minus I by h cross square root of 2me x, and the second wave function will be psi 2 equals to b e to the power minus I by h cross square root of 2me x. Now for these two equations we will apply the boundary condition. So the boundary condition, since the wave function is 0 everywhere outside the box, so that means the wave function will become 0 for the boundary condition on the boundary. That means when x equals to 0, psi x will be equal to 0, and similarly when x equals to L, psi x is also equal to 0. So these are the boundary condition. So we will apply the first boundary condition. So the first boundary condition is the wave function will become 0 when the position x equals to 0. So when x equals to 0, the psi 1 will also become 0, and hence putting the value, putting the first boundary condition to psi 1, we can write 0 equals to a into e to the power minus I by h cross square root of 2me into 0. So that is a into e to the power 0, that is equals to capital A, because e to the power 0 equals to 1. It implies that for the first boundary condition to be satisfied, the coefficient A should be 0, which makes psi to be 0, which in turn means that the probability density, that is psi star, psi 1 star into psi, would be 0 for the all values of x, so that the particle would have the 0 probability existing on the in the box, that is the particle cannot exist in the box. Similarly, when we apply the first boundary condition to psi 2 second wave function, we get the constant value b equals to 0, which again implies that according to the second wave function, psi 2 the particle cannot exist in the box. Thus, through psi 1 and psi 2 are the satisfactory solution. Thus, those psi 1 and psi 2 are the satisfactory solution to the amplitude wave equation. This does not satisfactorily apply for the boundary condition, and hence we will consider a new wave function, that is if a new wave function which are the linear combination of the two wave functions psi 1 and psi 2, and the new wave function, that is psi, so psi x equals to psi 1 x plus psi 2 x, and this is the new wave function of the particle inside the one dimensional box. And if we apply the first boundary condition to this new wave function psi, the first boundary condition is psi equals to 0 when x equals to 0. If we apply the first boundary condition to this new wave function, we will find that a equals to minus b or b equals to minus a. Now substituting these values, we can simplifying, we can write the wave function psi x equals to a into e to the power. E to the power means exponent. E to the power minus I h cross square root of 2me x minus e to the power I by h cross square root of 2me x. So that means here, here we are considering a equals to either minus b or b equals to minus a. That means only one constant will be there. So this is equation 33 gives a function that is solution of the Schrodinger amplitude equation and satisfy the first boundary condition. Now we need to import the second boundary condition. However, it is mathematically convenient to simplify the equation by defining a parameter. So if we define a parameter to simplify the equation, if we define a parameter that is square root of 2me by h cross x equals to y. So if we define a simple parameter, this equation will become psi equals to a into e to the power minus iy minus e to the power iy. Now, we will take the help of the Euler's formula to convert the complex exponential function. According to the Euler's formula, we know that e to the power minus ey equals to cos y minus I sin y. Similarly, e to the power iy equals to cos y plus I sin y. Now, subtracting equation 36 from equation 35, if we subtract this one from 36 from equation 35, we can write e to the power minus iy minus e to the power iy equals to minus 2I sin y. Now, putting these values, we can write psi equals to minus I 2a sin square root of 2me x by h cross, which is equals to c sin, because this one is constant, which is equal to c sin square root of 2me x by h cross, where c equals to minus I 2a. Now let us import the second boundary condition. If we apply the second boundary condition, that means the wave function will become 0 at x equals to L. So in place of x, we will put L. So the wave function will become 0. So 0 equals to c sin square root of 2me L by h cross. So the constant c cannot be 0 because that is one constant. So as c cannot be 0, that means this value will become 0. So therefore, the term sin square root of 2me L divided by h cross must be equal to 0. And again we know that the basic trigonometry, that the sine function is 0 when its argument is an integral multiple of pi. So here, so this will become, this function will become 0, sine something will become 0. That means if this value will be integral multiple of pi, that means sine pi, sine 2 pi, sine 3 pi will become 0. And hence, total this one will 0, that means sine square root of 2me L by h cross will be 0. That means square root of 2me L by h cross should be equal to plus minus n pi. And rearranging the equation, we can write square root of 2me by h cross equal to plus minus n pi by L. And hence, substituting these values, we can write the wave equation. So this is substituting the value from equation 40 in equation 38. If we put the value in equation 38, which is the actual wave function, the wave function will become psi equal to c sin plus minus n pi x by L, which is equal to plus minus c sin n pi L by x. So the wave function given in equation 42 is one, that is the solution of Schrodinger wave equation for the particle confined to move in one-dimensional box of length L and satisfy both the boundary condition. So here the plus minus sign here indicate that there are two satisfactory series of function. Both of these contain one function for each value of n. So this is the satisfactory solution of the particle move, solution to the Schrodinger wave equation of the particle confined to move in a one-dimensional box of length L, and the solution is psi equals to plus minus c sin n pi x by L. Now coming to the normalization condition, again we know that the normalization condition is like this, that is whole integration of psi square d tau equals to 1. Here that is whole integration of psi star psi d tau equals to 1. And for this, as the particle is moving in one-dimensional box, so the normalization condition will become one-dimensional box of length L. So the normalization condition will become psi star integration from 0 to L, integration from 0 to L, psi star psi d tau should be equals to 1. And here in the previous part we have calculated the solution for the Schrodinger wave equation which satisfy both the boundary condition, that is psi equals to plus minus c sin n pi x by L, and putting, and also its complex conjugate will be like, if psi is this, then psi star will be plus minus c star sin n pi x by L. So this is its complex conjugate. Now putting the value of psi and psi star, we can write integration from 0 to L. First one is psi and second one is psi star dx should be equals to 1. That is c sin n pi x by L, c star sin n pi x by L dx equals to 1. Implies that integration from 0 to L c star sin n pi x by L dx should be equals to 1. And again we know that 2 sin square theta equals to 1 minus cos 2 theta. So sin square theta equals to half into 1 minus cos 2 theta. Now substituting this value here, so we know that sin square theta equals to half 1 minus cos 2 theta divided by 2. So here we found that sin square theta equals to 1 minus cos 2 theta divided by 2. So using same formula for sin square n pi x by L dx, we can write the Schrodinger wave, the solution will become c star integration from 0 to L half into 1 minus cos 2n pi x by L dx, that should be equals to 1 according to the normalization condition. Now simplifying this, we can write c star whole into integration from 0 to L dx by 2 minus integration from 0 to L half cos 2n pi x by L dx, that should be equals to 1. Now integrating, we get c star integration of dx by 2, that is x by 2 from 0 to L, and similarly minus half cos 2 pi half half minus integration of half cos 2 n pi x by L. Integrating this value, we can write sin 2 n pi x by L divided by 4 n pi by L, so which is, that should be equals to n. And again applying the limit, so here the limit is 0 to L and here also 0 to L. Now applying the limit and simplifying, we can write c star L by 2 equals to 1. That means modulus of c square equals to 2 by L. So that means c equals to square root of 2 by L, and hence the substituting the value of c, that is plus minus square root of 2 by L, we can write the wave function psi equals to plus minus square root of 2 by L sin n pi x by L. and here we will take either the positive or negative version of the wave function to get the probability. However, as a matter of convention, the positive versions are generally used. So, the final expression for the normalized wave function of particle confined in one-dimensional box of length L will become psi equals to square root of 2 by L sin n pi x by L, where n equals to 1, 2, 3, that is the quantum number. Now coming, so this is the final expression for the normalized wave function of the particle confined in a one-dimensional box of length L. Now coming to one example, so that the wave function given in equation 55, this one, are actually the eigenfunctions of Hamiltonian operator for the particle confined to one-dimensional box of length L. So here we know that Hamiltonian operator in the x-axis, that is h cap equals to minus h square by 2m d square by dx square, and the wave function is this one. What we got the solution. So this is the final wave function and this is the Hamiltonian operator. Now we know that it will to be, if the wave function is eigenfunction, then h cap psi should be equals to E psi. Now substituting these values of h cap, this one, and substituting the value of psi, this one, we can write E psi. Now let us solve the left hand side of the equation. So this is the equation. First we will solve the left hand side of the equation. Now solving the left hand side of the equation, we will find that is equals to this one, h cross square by 2m n pi by L whole square of n pi by L psi, and substituting h cross equals to h by 2 pi, because we know that h cross means that is h by 2 pi, and simplifying we can write h square by 2m into square 2 pi whole square into n square pi square by L square psi, so that is equals to n square h square by 8 ml square psi, and hence the eigenvalue is n square h square divided by 8 ml square, which in fact the energy expression for the particle in one-dimensional box, and hence it is proved that hence it is proved that the final expression of the normalized wave function is an eigenfunction for the Hamiltonian operator with eigenvalue n square h square by 8 ml square. And here we will calculate the energy expression. So the energy expression En equals to n square h square by 8 ml square, where n equals to 1, 2, 3, 1, 2, 3, etc. So for the energy expression, so the value of the energy, that is En equals to n square h square by 8 ml square. Now putting the value of n equals to 1, we can write that is E1, that is the ground state energy of the particle, E1, that is equals to h square by 8 ml square, and putting n equals to 2, E2 equals to 4h square by 8 ml square, n equals to 3, E3, 9h square by 8 ml square, n equals to 4, E4, 16h square by 8 ml square. Now for the wave function n equals to 1, if we put n equals to 1, then the wave function will become psi equals to square root of 2 by L sin pi x by L will correspond to an energy of E1, that is equals to h square by 8 ml square, and it is the minimum amount of it is the minimum energy of that particle that can have, and that is called the 0-point energy. And again, we should so recall that when we define the particle in one-dimensional box, we assume that the potential energy to be 0 within the box. This means that the This means that the energy that the particle possesses is nothing but the kinetic energy, and it cannot be, and it can never be zero. That means the kinetic energy will not be zero. That can never be zero. The potential energy within the box will be zero. So it is a significant outcome, as it implies that the particle confined to box in a box, confined to move in a box of finite length, can never have energy zero. So it can never be at rate, even the temperature will be absolute zero. Since the state of the least possible energy, that is called ground state, that is called 0 point energy. So the 0 point energy is E1 equals to h square by 8 ml square. Now coming to one question, calculate the 0 point energy of an electron confined to move in a one-dimensional box of length 60 picometer. So that means here L equals to 60 picometer, which is equals to 60 into 10 to the power minus 12 meter. Also calculate the velocity of the electron, and we know that the mass of the electron is 9.11 into 10 to the power minus 31 kg. And here the 0 point energy for the particle confined to move in one-dimensional box of length L, that is E1 equals to h square by 8 ml square. And substituting these values, we can write E1 equals to 6.26 into 10 to the power minus 34 joule second whole square. So here we are putting the value of H divided by 8 into putting the value of mass of electron and length that is given in the question. So solving, we can write E1 equals to 1.494 into 10 to the power minus 18 joule. And again, we know that kinetic energy, that is the total energy, because the potential energy is zero. Hence, kinetic energy, which is equals to total energy, E equals to half mv square. So, half mv square, that is the total energy, and hence V equals to 2E square root of 2E by m, and the velocity of the particle 2 into calculated value of energy divided by mass of electron to the power half. That means square root of 2 into calculated value of energy in the previous part divided by mass of the electron, and after that we will find that velocity of the electron is 1.811 into 10 to the power 6 meter per second. And again, we see the energy expression En equals to n square h square divided by 8 ml square for the values of n to be 1 or 2 or 3, etc. Now another question, calculate the wavelength of the photon emitted when an electron confined to move in one-dimensional box of length 50 picometer drops from first excited state to the ground state. The mass of the electron is given. So here the energy first excited state means n equals to 2 and ground state means n equals to 1, and the energy difference daily equals to n square n daily means that is n plus 1 whole square minus n square whole into h square divided by 8 ml square, so which is equals to 2n plus 1 whole into h square by 8 ml square. And again we know that according to the Planck's formula, E equals to h nu, that is hc by lambda. Rearranging, we can write lambda equals to hc by E. So here lambda equals to hc. So writing the expression for daily, what we have solved here, we can write lambda equals to 8 cml square divided by 2n plus 1 whole into h. Now putting the values of C is the velocity of light, m is the mass of the electron, and L is the length of the one-dimensional box. Now 2n plus 1, that means 2 into 1 plus 1, and putting the value of h, we can write lambda equal, we can calculate lambda equals to 2.75 nanometer. And another question is that calculate the wavelength of the photon emitted when 1 gram glass sphere. 1 gram glass sphere is confined to move in a one-dimensional box of length 5 meter, drops from first excited state to ground state. So exactly, you will follow the same expression we will find the lambda equals to, for the 1 gram glass sphere, lambda equals to 3 into 10 to the power minus 28 meter. So here the wavelength will be extremely small because the particle is a macroscopic particle, that is 1 gram mass. But for electron, lambda equals to 2.75 nanometer. So here we will take 5 minutes of gap. Hello. So now we'll discuss the